Today in the workshop, we're looking at multimeters. We'll see how to choose a multimeter and how to use it to perform some useful tests. We'll also compare meters to see if the expensive ones are really worth the extra money. We're getting some accurate readings today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to go onto the workbench and work with the most essential piece of test equipment that there is, the multimeter. The multimeter is literally the Swiss Army knife of test equipment. It can do a bit of everything, and it is so useful when you are troubleshooting and creating electronic circuits. You can use multimeters to troubleshoot your wiring. You can use it to test the components within your circuit. You can also use it to make adjustments to voltage and currents. Multimeters can also be very useful around your home, so it's something everybody should really own. Now, if you're in the market for a multimeter, you've probably noticed the price range is very extreme. You can get multimeters for $25, you can get them for $2,500, and obviously there are a number of features included with the more expensive multimeters that you won't find in the cheaper ones, but do you really need them? And are the least expensive multimeters as accurate as the more expensive ones? Is it worth spending the extra money to get a name brand multimeter? We're going to figure that out today. What we're going to do is we're going to look at the multimeter. We're going to examine all of the features of a multimeter, and I'll show you how to use them. So if you've got a new meter and don't know how to use it, you're going to want to follow along for that. We're also going to put them to the test. We're going to test inexpensive ones against expensive ones and see how accurate they are. So sit back and let's learn a little bit more about the multimeter. In its basic form, a multimeter is an instrument that can measure voltage, current, and resistance. A modern multimeter, however, can measure several more parameters, making it an essential instrument for your test bench. Multimeters can fall into two different categories: digital multimeters, which are by far the most common these days, and analog multimeters, which are no longer really used much. Within the digital multimeters, we can also divide these into two categories: manual ranging multimeters, which require you to select a range you're measuring, and auto-ranging multimeters, which select a range for you. While all multimeters are different, there are many common components between them. All multimeters will have some form of a function selector to allow you to select the measurement function you wish to perform. Multimeters will have input jacks. These are banana jacks that allow you to connect test leads to the meter. The multimeter will have a digital display. This will display the measurement reading as well as other information. And there will be buttons for additional settings and selections. Another essential component of every multimeter are the test leads that connect to it. Virtually every multimeter uses banana plugs for its test leads, so you can exchange leads between different brands of meters. To measure voltage and resistance on multimeters, you generally connect your leads between the COM and the V lead. To measure current, you'll need to make a different connection, usually to a 10A or MA connection, as well as the COM lead. Today we're going to learn how to use a multimeter. We'll learn how to select a multimeter, and we'll perform some accuracy tests on a number of different multimeters. We'll learn how to read multimeter specifications, we'll look at a few multimeter accessories, and of course we'll cover that all-important multimeter safety. So if you find multimeters to be confusing, we're going to take the confusion away today. So let's go and start working with some multimeters. And here we have a collection of multimeters and a wide variety of features and prices. Now we'll start off with this one here. This is the oldest multimeter I have. Technically, this was probably the first piece of test equipment that I brought into the DroneBot workshop, and it even played a part in helping wire up the workshop. Now this is a manual ranging multimeter. In other words, when you're selecting resistance or voltage, you have to select the range that you're in. Now that can sometimes be inconvenient if you don't know approximately what range to go for, you have to start at the highest one and work your way down. But it also has advantages over auto-ranging ones in that if you're measuring a fluctuating voltage, the numbers and everything will stay the same, the decimal point, whereas on an auto-ranging multimeter, it'll quite often jump into a different range with a different decimal point, and you'll get a very difficult to read reading. So there is still use for a manual range multimeter. Otherwise, this is a basic multimeter, and it measures all the basic functions, resistance, voltage, current. It also measures capacitance, and it measures frequency as well. Now, over here, we've got an auto-ranging multimeter, and this has a number of different features on it. It'll measure all of the things I just mentioned before. It'll measure temperature, etc. Auto-ranging just means you flip it into what you want. You want to measure voltage, you want to measure current, etc. You put it into there, and it'll be up on the screen for you without you having to determine a range, and that's kind of nice. This is a pretty nice meter. I actually make a lot of use of it. Now, over here, we've got a meter that you can see is a bit different, and this is because it's got an inductive current sensor on it here. And so this is for non-contact current sensing, and I'll be showing you how we do non-contact current sensing in a little bit. Now, this is the newest meter that I've got here in the workshop. In fact, it's just a few days old, and this is one of these automatic, it does everything. You don't even have to tell it whether you're measuring voltage or current or resistance. It can figure it out, although you can manually set that. But this is also a 2-channel oscilloscope and a signal generator, so it's really basically an entire workshop in one package. And as I said, I just picked this up, and so I'm just starting to play with it. I just couldn't resist it. I kind of have shiny object syndrome. Speaking of shiny object syndrome, I did pick this up. I would not recommend it to anyone. Now, there are more expensive versions of this type of device, but this is a meter that's made for SMD stuff. You can essentially get around the contacts on the board and then read it on here, or that's the theory. It isn't a particularly good implementation, this one, and we won't be looking at it again. Plus, I have a better solution for doing that than using a meter like this. Now, back to the meters. This is a benchtop multimeter, and I love having a benchtop multimeter. This is AC powered. It's not battery powered, but having a meter on your bench all the time can really be very, very handy. So if you've got a permanent workbench situation, you might want to look at something like this. And finally, this is the flagship of my meters. It's the only name brand one I have. It's a Fluke, and for those of you who've been in electronics for a while, you'll know that Flukes are pretty well an industry standard. Back when I was a technician in the 1980s, every time you were assigned a toolkit, it always had a Fluke multimeter. And it's a very versatile meter. This is one of the lower price Flukes. Nonetheless, it's the most expensive meter of all of these meters here. So one thing we're going to do today is determine whether that extra expense was warranted when we check the accuracy of these things. But at any rate, you can see there's a wide variety of multimeters to choose from. Now let's go and take a look at a few accessories that we can add to these multimeters. So I have a number of multimeter accessories for you over here. Now, most of these were bought aftermarket, and accessories for one multimeter will fit the other one because accessories really are things that have to do with the probes, and the probes on multimeters all use the same standard banana plugs and banana jacks, so they're very easy to interchange things. Now, one accessory that probably came with your meter is this, and this is a thermal probe, and this is what you use to measure temperature on the multimeter. So you would just plug this in place of the regular probe and use the end over here to measure temperature with. You can also get different probes for your meters. These probes have interchangeable tips, and right now what I've got on them are insulation piercing tips. They're very sharp needle-like tips that can actually pierce through wire insulation, so you can take measurements without having to remove the wire. They have another use as well, and I'll show you that in a moment. Another tip you can get is one that replaces that really El Cheapo SMD measurement thing I showed you. This is just basically the same thing on a set of leads, and you can use that to measure like things that are on a circuit board. It's very, very handy actually. And most of these have to do, as I said, with banana plugs and banana jacks. And so banana cables are actually an accessory themselves, and you can get things to adapt them. And that's what I have over here. So you can get all these different ends that you can put on, and they just snap on to the banana end over here. I've got one that makes it into a lug, and here's another one that makes it into an alligator clip. The wrong color, but that's what it is. And I've also got these ones that turn them into the needle-sized ones. And these are very, very handy, as I said, for something else. And that something else is to use with solderless breadboards. These needles will fit perfectly into the leads on a solderless breadboard. So if you're taking measurements on a breadboard, these are very handy to have, either as an accessory for a banana or just basically on the end of some leads like I have over here. Another handy thing are these ones, and these have a little clip on the end of them, and they let you clip onto wire. I don't know if you can see the clip. It's very, very tiny. But if I take something like a resistor here, for example, I can grab onto it. It's a grabber. And so it lets you grab onto a lead. And that's really, really handy when you're trying to measure something and measure right onto a lead when something's in circuit. Another style of banana cable that I really like are these ones. And what I like about these is that the ends of these cables have also a banana socket on them. So you can just daisy chain these things. You can stagger them like that, and that's great when you have like a common ground connection or something and you're trying to hook more than one meter up. So you can get a lot of different accessories for your multimeter, and it'll really expand the things that you can do with it. Okay, now that we've taken a look at a bunch of multimeters, it's time to actually start working with them. So what we're going to do is we're going to take out our meters and we're going to go through all of the basic functions of a multimeter. We'll be covering the following basic functions: resistance, which also includes continuity and a diode check, DC voltage and current, AC voltage and current, frequency, capacitance, and temperature. We're going to begin by making a resistance measurement. In order to do this, we need to place the meter's function selector in the ohm or resistance position. We'll place the leads into the COM and the V jack on the meter. Measuring a resistor is quite simple. We'll connect our red test lead to the V jack and connect that to one side of the resistor. We'll plug our black test lead into the COM jack and connect it to the other side of the resistor. When measuring a resistor, lead polarity is not important because resistors aren't polarized. If you're going to test a resistor on a circuit board, make certain that you remove the power first. You may also need to remove one leg of the resistor to get an accurate reading, as the rest of the circuit can affect the resistance reading. Another function in resistance mode is the continuity function. When the continuity function is activated, the meter will emit a sound when it encounters a low resistance. This is great for troubleshooting purposes. Most meters also have a diode test function. This will display the voltage drop across the diode when you hook it up in the correct direction. When you hook it up in the other direction, you won't get anything. So now let's go use the resistance function on our multimeter. Now we're going to start off with a couple of very basic multimeter functions, and I'm using the fluke meter to demonstrate this just because it's got a very simple control on the front, just one dial and not a lot of writing on it so you can see what it's doing. But of course you could use any of these multimeters for these demonstrations. Now we're going to start off by measuring resistance. We're also going to check continuity, and we're also going to check a diode, and they're all in the same function here in the meter as they are in many meters. And so when I put it onto here, it's on resistance mode. You can see it says auto down here, so it's auto ranging right now, and it's gone up to megohms because of course my two probes are not connected right now, so naturally they don't have any resistance. Now I have a resistor across the board over here, and so we'll just connect to it using these probes. And we get a reading of 4.72, and this is a 4.7K resistor. Now it's at 4.71, so that's within tolerance, and so that's a very simple thing to measure resistance. Now we'll take that out and we'll move on to the next thing here, and this is continuity. You can see in the corner of the meter it's got a little thing that indicates it's going to make a sound, and basically it's measuring a resistance, but it's also going to give me a sound every time that I have pretty well down near 0 ohms. And that's a wonderful feature for when you're trying to troubleshoot some wiring. You don't have to actually look at the meter, you can just hear the sound. Now we're going to move up over here, and you can see the little diode symbol in the corner. We're in diode test mode, and of course a diode can let current go in one direction but not the other. So we'll go across this diode here, and we don't get anything on the meter. Now we'll reverse the polarity. And we get a reading 0.555, and that's the voltage drop across the diode. So the diode is working, it only conducts in one direction, and it also is giving us a reading. And I've also got another type of diode here, a light emitting diode, and if I go across the LED in one direction, we get absolutely nothing. It is a diode. Let's reverse the polarity there. And you can see I get a reading 1.785, and that's the voltage drop across the LED. And if you look at the LED, it's also on right now. So this is indeed a great way to test an LED. So here we've already started off with a meter, and we've been able to measure resistance, we've been able to measure continuity, and we've also been able to check both diodes and LEDs. So I'd say it's a pretty good start to show you how versatile that this instrument actually is. The next parameters that we're going to measure are voltage and current, and we're going to start by measuring DC voltage. In order to measure DC voltage, you'll need to place your meter in either the volt or DC volt position. If your meter only has a volt position, you'll need to select or auto sense DC. Make certain that you observe the maximum ratings for DC voltage and don't exceed them at any point. You'll place your two test leads in the COM and the V jacks to measure voltage. Now here's how we'd measure the voltage on a battery. We would connect our red test lead to the V jack and connect that to the positive lead of the battery. Our black test lead would be connected to the COM jack, and that would connect to the battery's negative terminal. When checking DC voltage, you need to observe the lead polarity, otherwise you'll get a reversed reading. Remember that your meter has a very high impedance and provides virtually no load. This means that when testing batteries, you're not going to get a very accurate reading. Some meters have a battery test function which provides a load. The next parameter we're going to measure is DC current. You'll need to place your meter into the A or MA position. You may also need to select or auto sense DC. Once again, make certain to observe the maximum current rating. You'll place your leads in the COM and into the MA or A jacks on your meter. Now here's how we'd measure the current that this transistor radio is drawing from a 9-volt battery. In order to measure current, we need to break the connection. We can then connect the COM lead to one side of the broken connection and complete the connection with the 10A or MA lead. Now, when it comes to measuring AC, we need to remember that there are different ways of expressing AC voltage. One method is peak to peak. This is the difference between the maximum positive and negative peaks in the waveform. The most common method of expressing AC voltage is root mean square, or RMS. This is the equivalent DC voltage that would produce the same heating effect in a resistor. Most meters use RMS, and many of them use true RMS. True RMS provides an accurate reading even when the waveform is not a sine wave. Some advanced meters allow selection between peak to peak and RMS. We're going to start by measuring AC voltage. We'll need to place the meter in the volt or AC volt position. On some meters, you'll need to select or auto sense AC. As always, we'll observe the maximum voltage rating, and as we did with DC voltage, we'll place our leads in the COM and the V jacks. Now here's how we'd measure the output of this transformer. We'd connect our red lead to the V jack and connect it to one side of the transformer output. The black lead will be connected to the COM jack and will be connected to the other side of the transformer's output. Since we're measuring AC, the lead polarity is not important. On some meters, you'll also display the AC frequency when you measure AC. And the last parameter that we're going to measure is AC current, and we're going to do a direct connection as opposed to the non-contact methods that I'll show you a bit later. For this, we'll need to place the meter in the A or the MA position, and you'll need to select or auto-sense AC if your meter requires this. Once again, we will observe our maximum current rating, and as we did with DC current, we'll put our leads in the COM and either the MA or AJAX, depending on how much current we're trying to measure. Now here's how we would measure the current on the light bulb connected to the output of the transformer. As with DC current, we need to break the connection. We'll connect our COM lead to one side of the break, and our 10A or MA lead to the other side. As this is AC, the polarity of the leads is not important. We're going to test our voltage and current measurement functions using this circuit. This is a pretty simple circuit which drives an LED from an AC input. It uses a 6-volt AC transformer, a bridge rectifier to convert the AC to DC, a 680 microfarad capacitor to smooth out the DC, and it uses an LED, and the LED has a 100 ohm resistor and a 1K potentiometer as its dropping resistor. You can adjust the pot to adjust the amount of current through the LED. We're going to use 5 different measurement points on this circuit. Measurement point 1 is across the AC voltage, so this will measure the AC voltage output of our transformer. Measurement 2 will measure the AC current consumed by our circuit. Measurement 3 will measure the DC current going to the LED. We can adjust this current with the 1K potentiometer. Measurement 4 will measure the DC voltage output from the bridge rectifier. And measurement 5 will measure the voltage drop across the LED. Now when properly operated, the LED should have a current of 20 milliamps and a voltage drop of 2 volts. So let's go wire this up and check it out with our meters. Now throughout this video, I've been trying to make the case for having multiple multimeters, and I think this is the ultimate example over here. Obviously, you could do all of this with one multimeter, but each of these meters is measuring one of the parameters in the circuit that we've just seen. Now, the first meter is measuring the AC voltage that is coming right off of the transformer, and you can see it's about 7.5 volts. This multimeter is measuring the current that we're drawing, and we're currently pulling about 23.5 AC milliamperes from this, so we're not taking very much current at all. This next one is also measuring current. This is the current that the LED is drawing, and this is what we can set with the potentiometer. And if you recall, the specifications on the LED are that the optimum are 20 milliamps of current, and it'll have a 2 volt drop across it, and over here is the voltage drop across the LED, and as you can see, it's 2.059, so it is indeed quite close to specification. And this is the DC voltage that we're getting on the output. Now we can do some interesting things here. For one thing, we can see how much that the output is affecting the DC voltage, how much the load of the LED is affecting it by just removing the LED from the circuit for a moment. Obviously these drop to nothing. You'll note that the current over here in milliamps is practically nothing as well, and this voltage has jumped almost all the way up to 10 volts. And so if I put the LED back on, we'll see that everything resets itself. And we can also adjust the amount of current that we're getting. So say that we wanted to draw a little bit less current from our LED, we could set the pot up over here, and the LED is going to dim a little bit, but we can actually get it down to about half the current, and we can still see the LED. And as you can see, the power supply voltage has risen as well. And we are still dropping about 2 volts across the LED. So you can do a lot of interesting experiments when you have multiple multimeters. But what I'm really trying to illustrate here is both the different settings that you can use for the meters to measure all the different parameters. And also, if you look at the breadboard, the different ways that I have attached it with the probes, with the bananas over here, with the clips across the LED, the ways that you can get at your circuit when using a multimeter, and that I think is the key point of this rather extravagant demonstration. Some multimeters have non-contact sensing functions. These allow you to sense alternating current without directly contacting it, and it comes in a couple of different forms. There are the current sensing clamp meters. These allow you to sense current flowing in wires without directly contacting the wire. There's also the NCV live function on some multimeters. The NCV, or non-contact voltage sensor, can determine if a wire is live without coming into direct contact with it. Now in this demonstration, we're going to use the clamping meter to do an inductive current test. And this is a great thing to be able to do because measuring AC current, especially high AC current, can be somewhat dangerous. So not having to actually get in contact with the wires is a good thing. And so what I'm going to do is put this into the current mode, and I've got two of them, a high current mode up to 1,000 amps and a lower current one that says 60 or 600 amps. You get two ranges over here. And these currents are normally for fairly high currents. You're not going to be measuring milliamps or anything with them. I'm going to put the function onto AC mode over here. So it's on AC now. Now I'll show you how this works. I've got a soldering gun and it's plugged in to this assembly over here, which is just an AC plug that's also got its 3 wires split out here, and you'll see why in a moment. Now first I'm going to put the meter around here. I'm going to put this on, and I don't get anything at all on the meter, if you can see that. But that's because that's not how it works. So I'm going to put it just around the hot lead, which is this one over here, and turn it on, and there you go. I've got about 1.17, 1.15 amperes of current, which for a 150 watt soldering gun at 120 volts is probably about correct. And you can also measure this down on the neutral side as well. It'll measure over there as well, but of course it will not measure on the ground. You can't expect anything there, and naturally you don't get it. So inductive current sensing is a very handy thing to be able to do. It's a very safe thing to be able to do. Just remember, you need to be sensing one of the wires. If you try to do both of the wires, they'll cancel each other out and you won't get any reading at all. Now these two multimeters have a feature called NCV, or non-contact voltage sensing, and that can be a very handy feature to look for in a multimeter if you're an electrician or if you do a lot of electrical work. What NCV lets you do is sense the presence of voltage without actually having to have any contact. Now it doesn't measure the voltage, it just gives you a rough idea of the level of it and whether it is there or not. And so it's great for finding out if an AC outlet is live or not. Now in both of these meters it works the same thing. You put it into NCV mode and then it goes and senses the voltage. I'll try it with this one here. Now right now I've got it in NCV mode and I'm placing against the power bar that currently is off and I'm not getting any reading. If I turn it on, I'll get a reading and it says low over here because it doesn't see that high, but if I move it to this one, it sees high. So this one is actually sensitive enough to see the hot lead and the neutral lead of the power, which is pretty cool. And so it lets me know that there's power here or that there's power not there, and prevents me from having to actually measure it. Now, if you are determining this so that you can work on the AC line, you would definitely want to measure the voltage just to double check. But it's a great way to know whether an AC outlet is active or not. And it's a cool feature to have in a multimeter if that's something that you need. Most multimeters have a function for checking capacitance. You'll find a cap or capacitor symbol or microfarad position on your selector switch. To measure capacitance, you'll place your leads in the COM and the V-jacks. Measuring a capacitor is pretty simple. You'll take the red lead connected to the V-jack and connect it to the positive side of the capacitor if it's polarized, otherwise just connect it to any side. The COM lead will be connected to the negative or other side of the capacitor. Make certain that you check polarity when you're using a polarized capacitor. It's a good idea to discharge large capacitors before measuring, or your reading accuracy may be affected. Never measure capacitance in a live circuit. Always remove the power before measuring a capacitor. I'm going to use the benchtop multimeter to test capacitance, and I've gone to my parts drawers and taken a couple of drawers of capacitors out to test with. Now these are supposed to be 1 microfarad capacitors. We'll start with that. Now I've set the meter into its capacitance position, which in this case is just as simple as pressing this, and I'm using these short test leads, and it's actually a good idea to try to use short test leads when you're testing capacitance, because the capacitance of the test leads themselves will come into play, although when you're working with a value like 1 microfarad, that's pretty negligible. When you're down at some very low values of capacitance, though, that is an issue. Now, this is a polarized capacitor, and so I'm going to need to observe polarity, and on these, the longer lead is the positive, and the lead that's marked off is the negative, so we'll connect our positive here, and our negative here. And we'll watch the meter and notice it says overload. What it's doing right now is it's measuring the capacitance. It takes a while to measure capacitance. It's not instantaneous, because what it does is it charges up the capacitor and then it discharges it, and it measures the amount of time it takes, and that's how it calculates capacitance. And this is just a little below 1 microfarad according to this. I'll take another one from the same drawer because tolerance on capacitors is actually pretty awful. Okay, this one, let's see how it does. Again, we have to wait for a reading with the larger capacitor. And it's almost a microfarad as well. Now let's go to this one here, and I've got 2 values on here. The back value is 470 nanofarads. Now these are not polarized, so it doesn't matter what lead connects to what side. So we'll connect the 470. And I get 435 nanofarads, and we could try another one as well. And this is actually great if you're working on some kind of radio or audio circuitry where you're trying to match capacitors. You can get a few out of your drawer that matched perfectly. This is 437.8. So it's very easy to measure capacitance. As to how accurate the readings are, I'm not exactly certain, but this meter has a fairly wide range. You'll find a lot of meters, though, don't have a wide range of capacitance, and there are better methods of testing capacitors, meters that are dedicated for that. Nonetheless, just for testing capacitors on circuit boards or for matching up capacitors, having capacitance testing is a very handy thing in a multimeter. The next parameter that we're going to measure is frequency. Not all multimeters have a frequency measurement function, but if yours does, place your selector switch into the frequency position. You'll need your leads in the COM and the V jacks. Measuring frequency is pretty simple. You'll place your red test lead in the V jack and connect it to the hot or active lead on your frequency or audio source. The COM lead will be connected to the ground side of your frequency source. You should note that some meters have a pretty limited frequency range, as they're not really dedicated frequency counters. Now what I'm displaying to you here is my manual ranging multimeter, and specifically you can see it's pointing at the frequency measurement, and it says 20 kilohertz, and that's because that's the maximum frequency that you can measure with this multimeter. And that's not uncommon. All the multimeters I have over here, with the exception of one of them, really can't measure very high frequencies. This is the exception. My desktop multimeter is actually measuring 20 megahertz right now. It's being fed a signal, a sine wave of 20 megahertz. It's giving me the duty cycle of the sine wave as well. And so that's pretty good performance, although it doesn't compare to a full-fledged frequency counter. My counter can go to 2.4 gigahertz, and this tops out at about 20 megahertz. Otherwise, this meter isn't too bad. It tops out at about a megahertz, and this one here goes to, I believe, about 80 kilohertz before it stops. And the thing is, frequency counting isn't something you really buy a multimeter for. In fact, it never used to be included in multimeters, but in recent years they started to add it because being a digital circuit, it's not that difficult to do so. You could use the frequency counter in a multimeter to verify line voltage frequencies, of course, 50 hertz, 60 hertz, maybe 400 hertz. They're great for that. And for audio work, they're okay. They don't have that many digits. This one here, again, displays the most digits, 5. 5. The other ones are pretty well 4 digits. But for most work, they'll be fine. Certainly not for radio work or anything where you're doing timing accuracy. But for general purpose, when you do need to know a low frequency, an audio frequency, perhaps a music frequency for tuning an instrument, they would be fine for that. But otherwise, I wouldn't go shopping for a multimeter if you're really looking for a frequency counter. Many multimeters have a function to measure temperature. If yours does, place your meter selector switch in the temperature position. In order to measure temperature, you're going to need a thermocouple sensor, and there was probably one included with your multimeter. On some multimeters, there's also an internal temperature sensor just to measure the ambient temperature. If you have a thermocouple sensor, plug it into the COM and the V jacks. Measuring temperature is pretty simple. All you need to do is plug your thermocouple into the COM and the V jacks and place the thermocouple end on the device whose temperature you wish to measure. You'll find that thermocouples respond very quickly and will give you a very accurate temperature measurement. Now I've got my thermocouple hooked up to my clamp meter, and this is the thermocouple. You can see the end over here is the actual thermocouple sensor. And you can see that it's reading the ambient room temperature right now. It's a little bit warm inside here, 25.4. It also gives a reading in Fahrenheit above there. Now here we have a Raspberry Pi, and it's been running for about maybe 15 minutes. Now this Raspberry Pi doesn't have a micro SD card in it, and there's nothing, as you can see, connected to it other than the power supply. So it's not really doing anything. Nonetheless, it's starting to heat up. So I'm going to take a reading of the tip over here on the Pi just by touching that, and you can see it goes up instantly. Thermistors respond very, very quickly, and it's about 51 degrees Celsius or 125 degrees Fahrenheit, 52 degrees Celsius. Rather hot little piece of pie over here. And I'll remove the thermistor from it, and you can see the temperature rapidly falls. As I say, these things are very quick to respond. And so these are really great for troubleshooting on boards where you think you might have a component overheating, because you can narrow it down to the exact one with this very fine tip of the thermistor. So measuring temperature is actually a very handy function in a multimeter. Shopping for a multimeter can sometimes be a bit confusing. There are so many features in multimeters. There also are specifications, some of which make sense, some of which don't make a lot of sense. How do you choose the correct meter? Well, the good news is you really can't make a bad choice. Multimeters these days are great. Even the most inexpensive multimeter is an ideal tool for your workbench, so you really can't go wrong, but of course you want to get the most value for your money. So what we're going to do right now is show you how to read the specifications of a multimeter, and then I'll show you a few advanced features that some of my meters have that you might want to have on your multimeter. A good multimeter will come with a very long list of specifications, and you can break those down into the following categories: accuracy, resolution, input sensitivity, input impedance, the input ranges, sampling and display rates, and safety ratings and features. Accuracy defines how close a measurement is to its actual value. It's expressed as a percentage of the reading. An accuracy measurement also includes additional counts. You'll find accuracy listed for each function on the multimeter. Resolution is defined as the smallest change that the meter can display. This is related to the number of digits on the multimeter. A 3.5-digit multimeter has a maximum display of 1999, the 1 being considered the half digit. This can also be expressed as counts. We define sensitivity as the smallest detectable input change for a given measurement function and range, so there will be several sensitivity measurements in a multimeter spec sheet. The unit used depends upon function. A multimeter's impedance is the resistance that it presents to the circuit as it's measuring it. You want as high an impedance as possible in order to avoid loading the circuit down. Impedance is expressed in megohms. The range are the minimum and maximum values that the meter can measure for each function. Manual range multimeters will have a series of ranges specified. You'll find separate range specifications for both AC and DC functions. The term sampling can actually be used for two different things on a multimeter. It can refer to the analog to digital converter sampling rate. That converter sampling rate is always specified with a bandwidth. Sampling can also refer to the display refresh rate. How many times is the display changed per second? One of the primary safety features in a multimeter is a fused input or inputs. These are usually found on the current inputs. Multimeters are also rated with a category or CAT rating. Common CAT ratings for multimeters are CAT 2, CAT 3, and CAT 4. There are also other features that you may look for when looking at a multimeter. True RMS allows more accurate readings when the signal is not a sine wave. A backlit display can make the meter easier to view in low light. Auto ranging is a convenient feature that's easier to use than manual ranging. A data hold feature will freeze the display so that you can look at it when it's more convenient. Some multimeters have a USB interface that can be used with PC software or a spreadsheet. Many multimeters also have a bar graph display that makes it easier to visualize fluctuating signals. Now let's take a look at a few of my multimeters. Now, specifications are, of course, very important when you're selecting a multimeter, but it's not the only thing. I've got all the multimeters that we're working with today out, and each of them is rather unique. They all perform the same basic functions, but they all are unique in their own special little way. Now, this is probably the most unique one, of course, the clamp meter. And one thing aside from the clamp that makes it unique is it only has 2 input jacks. The other ones all have 4 of them. And that's because this one doesn't measure current directly. It relies upon the clamp. It relies upon inductive measurement for that. This is really more of a multimeter that would be assigned to someone like an electrician rather than in electronics. So if you do a lot of wiring around the house, etc., or if you do industrial wiring, then this is the kind of meter you probably want to get. If you do have a permanent workbench setup, I would highly recommend getting a desktop or a benchtop, multimeter. The fact you'll never need to replace the batteries is a cool thing, but it's always nice just to have one on your bench. Now, I actually had to modify this one. It didn't tilt up enough, and so I added a couple of extra feet onto it here, but other than that, it's been a great thing to have. Now, there are other unique features in all of these meters. One that 2 of these share, my oldest one and this one, that I really like. I'll demonstrate for you over here. Now, I'm just going to turn it on to a function. Right now it's millivolts. After it boots up, note over here the way that it's flashing. It's telling me that's where the test leads go. And so if I go into a current function, it's telling me the test leads need to be changed over here. And that's a very handy thing to have, because if you are, for example, measuring current and then go back to measure voltage, you need to remember to change those leads over to the correct position. Otherwise, you'll learn how to replace the fuse inside your multimeter when you short out the voltage. So very handy to have. This little meter here, my oldest one, also has a similar feature on it. The Fluke multimeter, one thing I like about it, those 2 things I like about it. First of all, it is quite simplistic to dial. It's not as busy as everything here. So this is great for an educational setup or where you're dispensing multimeters out to a crew of people, which is probably why I always got them in my electronics kit when I was an electronics technician. They're very simple to use. It's very obvious how they're used. They're also extremely durable. This multimeter weighs more than any of these meters here, including the benchtop one. It's obviously got something inside it that's very solid, and that's one thing they are. They're rugged and they're reliable. So if you're out in the field or if you're using multimeters in an educational setup, this is the kind of meter I'd go for. If I could only choose one, it would be a difficult choice, but I'd say this one does encompass most of what you need, and the price is certainly right. It's about $35-40 US for one of these. And don't get hung up on the brand name, by the way. When you're looking for user manuals models, for example. This one over here, I couldn't find it under this manufacturer's name, but I found it under this manufacturer's name. Look for the part number because they're all basically using the same parts and putting together meters. And you'll notice that when you're shopping for them, you can often see the same meter advertised by different manufacturers. But that's a great thing. That just brings down the price and does keep the quality up. And finally, this all-in-one thing might be a great thing to have as a second meter. I would get this as a first meter and then decide on either something like this or maybe a bench multimeter. But, you know, everyone's unique and your selection might be different. You'll notice, though, I'm pushing the fact that you probably need two multimeters. You'll find there's a lot of situations where you're measuring voltage and current simultaneously, and that's great to have. But the good news is you can't really make any wrong choices when you're out selecting a multimeter. They all will give you a lot of value, and they all have a lot of features that you can use on your workbench. Now I'd like to demonstrate a feature that I find very useful in a multimeter, and one of these meters has it and one of them doesn't. Now to demonstrate this, I've simply got a potentiometer. This is just a 100K pot, and it's wired up to a couple of test leads. I'm going to put them into the fluke, which is measuring resistance, which is what you'd expect to measure from a potentiometer. And it does indeed measure my resistance. And I'm moving it up and down a little bit. Now what I'm doing is I'm simulating a fluctuating reading. And as you look at the numbers, they're really all over the place. It's a little hard to gain any information from that. Now I'm going to move this to the other multimeter and do basically the same thing. So we get a reading. And I'm moving it up and down. But one thing you might notice about this display that the other display doesn't have is at the bottom, I've got myself a bar graph. And the bar graph is very handy when you have a fluctuating reading. Now I'm using resistance, but it also will work with voltage and current. And I find that to be a very great feature to have. So when you are looking for a multimeter, you might want to consider getting one that does have a bar graph display as well. And so now we come to that moment that you've all been waiting for, the great multimeter showdown. As you've noticed, I have a variety of multimeters, and they span a range of prices, and they have a number of different features. But at the end of the day, the thing that matters the most is, do they give accurate readings? So I've got some calibrated test sources. We're going to check out all of our multimeters. We're going to see how the cheap ones fare against the more expensive ones in our great multimeter showdown. And so we're going to begin our showdown with a resistance test. And what I've got here is 5 multimeters that are all testing precision resistors. And they're testing a 1K 0.1% tolerance precision resistor. So this resistor should have a value of anywhere between 999 and 1001 ohms. And I think you can see that all of these meters are pretty well within that range. This one is a little bit over, but I also want you to consider the test leads that I have here. These test leads are going to be adding some resistance as well. And of course, on any of the resistance tests, that needs to be factored in. So I'd say that everything here is pretty capable of measuring the 1K precision resistor. Now let's go and try a few other values. And so for the second of our resistance tests, I'm using a 10K precision resistor. And so this is a 10K 1% tolerance precision resistor. And so it should have a value within 10 ohms of that value. And I think you can see everything here is pretty well within there. These two are a little bit out, but not by very much. I think you could pretty well say that everything here is capable of measuring 10K. I have to say I've been pretty impressed by this little clamp meter because it's been bang on for both of our tests, and once again it is. And this one, of course, is measuring down to an extra digit of precision. So we're going to do one final resistance test, this time with a bit of an oddball value resistor. And so for our final resistance tests, I have a value which may seem a bit odd, but it's actually very popular when used with digital to analog converters. And the value of my precision resistor is 499 kiloohms. And as you can see, everything here is reading pretty close to 499K within the 0.1% tolerance of this resistor. So I would have to say that all of these multimeters are quite capable of accurately measuring resistance. I wouldn't really give give any one of them a particular advantage on it. Perhaps I would assign an extra point to the bench multimeter because it has an extra digit of precision, but I think all of these are capable of measuring resistance quite well. Now our next showdown is to test accuracy for DC voltage measurement. And in order to do this, I've used a module from Adafruit. This module is a voltage reference module, and it's made for analog to digital and digital to analog converters. It takes an input of 5 to 12 volts and produces two outputs, one at 2.048 volts and the other one at 4.096 volts. Now those may seem like odd voltages until you look at those numbers a bit more carefully. Then you'll realize how useful those would be for something like an analog to digital converter. And so I've got that wired on a solderless breadboard, powered up by a 9-volt battery, so we've got a nice power supply that doesn't have any ripple or noise in it. And I've got the two outputs wired up here. I've got the 4.096 output over here and the 2.048 volt output over here. And what we're going to do is we're going to feed that into the meters individually and see how accurate they are. Now, as you can see, I'm already using my benchtop multimeter and feeding the 2.048 into it, and it is very accurate, 2.0483 volts DC. And so we can move this here to get the 4.096. And I get 4.0905, which is close, but not exactly 4.096, but all in all, not too bad. Now let's take another meter and give it an equivalent measurement. So we'll plug into this meter. And this is the 4.096, if you recall. And can you see that? 4.094, that's pretty darn close. Okay, let's see what the other voltage is. And that's supposed to be 2.048. It's 2.049, 2.050. I'd say this meter is actually reading very accurately. Quite impressive, actually. Okay, let's go over to the Fluke. Now, this, of course, is our most expensive meter. And right now, we're feeding it 2.048. And 2.054, it's close, not exact, but it's pretty close. And the 4.096 is actually 4.103, so off by a little bit, not too much, but a bit. And remember, that is the most expensive meter I've got here. Now let's turn this thing on and put it into multimeter mode. And my 4.096 is reading 4.095. That's pretty good. Now let's see what happens with the other voltage here. My 2.048 is 2.051, so this meter is also very, very close. And finally, the last one is this. And we'll feed into here. And 2.052, where it should be 2.048, very close. And 4.099 instead of 4.096. So also very close. So all of these meters were very close. This one in particular was quite accurate, as was this one for the 2.048 volt. It was very accurate. The Fluke actually was probably the least accurate, which is surprising since it's the most expensive multimeter over here. And you could repeat this test with different voltages as well. Adafruit only sells this module, but Texas Instruments actually sells the chips on this, and they make them up to 10 volts, and they're precision down to 0.1%. So if you need a precision reference, it's a good thing to use as well. And so there you go. All of our multimeters are quite accurate for measuring voltage. Now the next test we're going to do is capacitance, and it's actually a pretty difficult test to do. Not that it's difficult to measure capacitance on any of these meters, it's quite simple to do that. But what's difficult is to get an accurate reference capacitor. They do sell mica capacitors, which are very high tolerance, but they're extremely expensive. It would be over $100 per capacitor to get a reference capacitor that's within the range of all these multimeters, because the cost goes up as the value goes up, and most mica capacitors are very low value. So I didn't think it was worth spending $100 for one capacitor that I would use just once to test a bunch of meters, many of which were worth less than the capacitor itself. So what I've done is I brought another meter into the picture. This is what's called an LCR tester, and it's a very inexpensive manual ranging one. You can get much better ones than these. And while it's not necessarily more accurate than the capacitance testing function in these multimeters, it does have a number of advantages, the main one being the range that it has. And it can go down into the picofarad range, whereas most of these meters here can go into the nanofarad range at best. So for low value capacitors, something like this is really handy. Another thing it has, which I like quite a bit, is that you could insert the capacitor directly into here. And being an LCR tester, it also tests inductance and resistance as well, so it's good for that. And another great feature is this zero adjustment here. This lets you compensate for the capacitance in the leads by zeroing the display, so it's pretty handy. So what I have here is a 10 microfarad capacitor that's, I think, pretty close to 10 microfarads. And we're going to start it off on this meter and then see how the other meters fare. And this one reads 9.96, and it actually reads pretty fast compared to the other meters for capacitance. Now I'm going to go to the benchtop multimeter first, and we'll plug in our leads. And of course this takes a little time. It's charging and discharging to make a reading. And this is 10 microfarads, and it reads 9.90 microfarads, pretty close to what that one read as well. Now let's give the fluke a try. And we'll just bring it where we can see it somewhere. 10.08 microfarads. It reads a little bit higher than the other ones, but otherwise certainly within the ballpark. And our fancy oscilloscope all in 1 meter. .44. It also reads a bit high, but again within tolerance. Let's go to the clamp meter. And we'll put it where we can see it. 10.25. It also reads a bit higher than what the LCR reads. And last but not least, this meter here. And what are we going to get here? 10.23. So it kind of jives with this one here. So they're all within the same ballpark, and really when you're testing capacitors, it's quite often not the exact value you want. You just want to find out if the capacitor is working or not, or you're trying to match up capacitors for audio circuitry. And for those purposes, any of these meters would work fine. If you need something to measure a wider range of capacitors, though, you might consider something like this LCR tester, and you'd also have the ability to measure inductors as well. And so that about wraps up our look at multimeters for today. I hope you enjoyed it. I hope you learned something, and I hope it'll help you choose your next multimeter. And remember, the best accessory for a multimeter is another multimeter. You'll really find it versatile to have more than one of these devices on your workbench. Now, if you want a bit more information about multimeters, there's an article that accompanies this video on the DroneBotWorkshop.com website, and you'll find the link to that article in the description right below this video. While you're on the website, if you haven't yet, please consider signing up for my newsletter. It is not a sales letter, it's just my way of letting you know what goes on in the workshop and giving you a preview of what's going to happen in the next videos and articles. If you'd like to discuss multimeters or show off some of the meters that you've got yourself, a great place to do that is the DroneBot Workshop forums, where you'll find a bunch of like-minded individuals who enjoy working with electronics and can help you out with your electronic projects or just like to talk shop. And of course, it's free to join the forum. And of course, if you are in a subscribing mood, please subscribe to the YouTube channel if you haven't already. I make videos about electronics and microcontrollers, and if you like this video, I'm sure you'll enjoy the other ones. All you need to do is click on that red subscribe button, and if you also click on the bell notification, you'll get notified every time that I make a new video. So until we meet the next time, please take care of yourself, please stay safe out there, and I will see you soon here in the DroneBot workshop. Goodbye for now.